Hello everyone. In this lecture, we want to discuss limits of piecewise defined functions. You remember that piecewise defined functions are functions that have different definitions over different intervals. It's not like we say, okay, a function has a definition of y equals x squared and that is it. And this is the definition over the set of real numbers. That's not correct for piecewise defined functions because in these kind of functions, we have more than one definition for a function. You may have two definitions, or you may have three or four or even 10 definitions for a function. But the thing is that these definitions of the functions are valid or they are defined for different intervals. This is an example, f of x equals x squared. That's a quadratic function, but only if x is less than or equal to 1. So within that interval, when x is less than or equal to 1, the definition of this piecewise defined function is y equals x squared, whose graph is like a parabola. You see, this is an example of a parabola. This is the graph, and we draw this up to 1, and then including 1. So you see that there's a solid dot here, not an empty circle, which means that at x equals 1, the definition of the function is y equals x squared. So 1 squared will be 1, and that is why the coordinates of this point is actually 1, 1. And then the second definition of the function is f of x equals 3, but that is the definition only if x is between 1 and 2, excluding 1, including 2. So you know that y equals 3 is a horizontal line parallel to the x-axis. It's called the constant function. And the line goes all the way from left to right. However, because this is the definition only within this interval of 1 to 2, that's why we start at 1 and we end at 2 only. We are excluding 1 because if x is 1, that is not the definition. But when x is equal to 2, that is the definition. Therefore, we have an empty circle on the left-hand side, or we have a hole, but then on the right-hand side, we do have a solid dot. And then if x is greater than 2 only, then the definition of f of x is y equals x, which is like the angle bisector of the first and third quadrants. So it's this line, y equals x, but we draw it only starting at x equals 2, excluding x equals 2, and then to the right as x is greater than 2. So this is the graph of this piecewise defined function. In fact, as you see, we have lots of holes, lots of discontinuities, and there's like three types of graphs involved here: constant function, linear function, and quadratic function. We want to find the limit of this function when x approaches 1 from right-hand side. So 1 is here. From right-hand side, the graph is not y equals x squared. The graph of the function is actually y equals 3. So when you want to find the limit of the f of x when x approaches 1 from right-hand side, then the answer is going to be actually 3. But if you want to find the limit of f of x when x approaches 1 from left-hand side, so that means that x is approaching 1 from values that are less than 1, such as 0.999, you see that we are moving actually on this curve, which is a parabola. So the answer would be 1 in that case. In general, what is the limit of f of x when x approaches 1? Not necessarily from right side, or not necessarily from left side. Well, we're going to say this was the right-hand limit and this was the left-hand limit. So because the right-hand limit was not equal to the left-hand limit, therefore we say that this function does not have any limit. So the limit does not exist. In the past, we had cases where the value of the function would approach infinity, and we would say the limit of the function doesn't exist because the value of the function becomes extremely, extremely large, for example. But this is the second scenario when we say the limit of a function does not exist, and that is when the right-hand limit and left-hand limit are not equal to one another. Right-hand limit is 3, left-hand limit is 1. Clearly, they're not the same. Therefore, the limit of the function when x approaches 1 in general does not exist, period. The limit of f of x when x approaches 0 from right-hand side. 0 is right here at the origin. From right-hand side, well, the answer is going to be 0. And in fact, it doesn't matter if x approaches 0 from right side or from left side. It doesn't matter. The answer is going to be 0 anyway. Limit of f of x when x approaches negative 2. So negative 2 is right here. It's on the parabola. So negative 2 all squared is going to be 4. So that's a point on the parabola. So if x approaches -2 from right side, so like this, or from left side like that, it doesn't matter because the limit is going to be 4 anyway. So we're going to say the limit is 4. Right-hand limit is 4. Left-hand limit is 4. The limit of the function in general is 4 when x approaches -2. And right-hand limit equals left-hand limit, and we will never say limit doesn't exist in this case. But in that case, we did say that. X approaches 2 from right-hand side, so 2 is here. From right-hand side, x approaches 2 from right-hand side, the limit of the function would be 2 on the right-hand side. But on the left-hand side, because we're taking that other function, y equals 3, the limit is actually 3. And in general, the limit, of course, does not exist because of the same reason we said. The right-hand limit is 2, the left-hand limit is 3, and they're not equal. Therefore, limit does not exist. Limit of f of x when x approaches 2 doesn't exist. Another example here, this is a rational function, and it says if x is not equal to 2, that's the definition. But if it is equal to 2, f of x is equal to 1 over 4, which is a constant. So this is another example of a piecewise defined function, but this time we have only 2 definitions instead of 3 definitions like the past example. So what we're going to do, we're going to say, okay, limit of f of x when x approaches 2. Now, from right side or left side, it doesn't matter. We have to use that first definition because here it says x is not equal to 2. If x is not equal to 2, that's the definition. So it doesn't matter if x is larger than 2 or less than 2. In either way, we are using that single definition for f of x. So if I write that down, x squared minus 4, x cubed minus 8, x approaches 2, we see that this is, of course, indeterminate form. Therefore, we have to find the limit using one of the techniques we have learned in the past, such as factoring technique. So I'm going to factor the numerator using difference of squares. I'm going to factor the denominator using the difference of cubes identity. So that is going to be 4, and that's going to be 2x, and x approaches 2. Okay. We need to know previous math knowledge. Like we need to know factoring, we need to know difference of cubes, sum of cubes, difference of squares, all those identities, all those formulas. This course is not a course where we talk about basics. We are actually using the basics here. So that's the factored form of the denominator. When you cancel out x minus 2 from top to bottom, you get x squared plus 2x plus 4, x approaches 2, and now the numerator approaches 4, I believe. The denominator approaches 12, and that means 1/3 is the answer. So the limit of the function is 1/3 if x approaches 2. Now, it doesn't matter from right side or left side. Now, it's interesting here to say that f at 2 actually, f at 2 is equal to 1/4. So the value of the function at x equals 2 is 1 over 4, but the limit of the function when x approaches 2, doesn't matter from left side or right side, is equal to 1 over 3, okay? So this tells us that there is some sort of discontinuity involved here in the graph of this function, if somebody graphs this piecewise defined function. But that doesn't matter. We don't want to go into that discussion of continuity. That's totally separate lecture for itself. But for now, we say that limit of f of x when x approaches 2, either from right side or left side or in general, is equal to 1 over 3, period. Okay? So I hope you understood how we find the limits of piecewise defined functions. Thank you for your attention and keep practicing as always.